if I'm working with two pulleys, I'd like to figure out which direction, and the wording that people use is, what direction does the system tend to go in? And so when I look at this, I don't want to just say the system tends to go down. When it comes to pulley systems, we're talking about a system that goes around a corner. And so it's either going to go around a corner to the left or it's going to go around a corner to the right. So when I look at this one, is this one going to go to the right or to the left? How many people say left? How many people say right? Going to go right. Why is it going to go right? What's the logic? Yeah? Yeah, the heavier weight's on the right. That makes sense. So what we're going to end up having is a system that goes this way. We're going to define this to the right, and we'll define this as to the left. Now, whenever we're defining directions like this, we actually are defining a reference frame. This is different than any other reference frame we've done before. This is a reference frame that goes around a corner. We've never dealt with reference frames that go around a corner before because we've never dealt with pulleys before. And so we say, look, this is a reference frame where I'm going to call to the right positive and to the left negative because it seems to me that the system's going to go towards the right, so why not make it easy on myself, right? And before we go any further with this, I want to write down my simplifications or my assumptions. Pulley simplifications. And it could be that we make our pulley understanding more complex and robust later on. But for now, we are going to deal with a frictionless pulley. That matters because we don't have to deal with the friction that would happen at the axle of the pulley. We're going to deal with an unstretchable rope. Again, that matters because mass 1 might get left behind if we don't acknowledge that we're going to consider this to be unstretchable. We're also going to deal with a massless rope. I'm going to think about why that matters. Think, if there was more rope on the right than on the left, and there will be more and more rope on the right than on the left, then the rope would actually contribute to the motion too, right? So let's pretend that this is like massless fishing line or something like that, okay? Thread. That's not quite realistic, but neither is having a frictionless pulley. So we're just kind of going to roll with this for now, okay? We could make it more complex later. It actually turns out having something other than massless rope becomes a very challenging calculus problem. So that's outside of our wheelhouse right now. We're not there yet. We're going to also ignore drag. Well, we're used to ignoring drag. We've done that with projectile motion in the past. And we're also going to have a pulley wheel that's massless. And people say, well, why does that even matter? Because the blocks of wood or bricks or whatever these are the things that's driving the system. Why do we care about the pulley wheel being massless? Well, it turns out that if you have a wheel that's rotating, once it gets spinning, it tends to keep spinning. They call it rotational inertia. Just like objects that are moving in straight lines tend to keep moving in straight lines. And if you want to test your belief in that concept, try turning your bicycle upside down. If you turn your bicycle upside down so that the wheels are up in the air, I don't even know how this works out as a bicycle. Let's just pretend that this is a bicycle that's upside down. But if you take your bicycle and you put it upside down and you spin those wheels, spin the front wheel because it doesn't have the gear chain attached to it, spin that front wheel super, super fast. How many people have done that before? Really? One person, two, three, a few people that have played with their bicycles. And sometimes when you turn your bicycle upside down and you do this kind of thing, you spin the wheels really fast, you're tempted to stick your fingers into the spokes. Anybody been tempted to stick your fingers into the spokes? If you do, that would be a good way to test rotational inertia. Because that wheel is going to tend to keep on spinning, agreed? And your fingers are going to tend to get sliced off by the spokes. And that would be a really good lived experience. At least you'd believe in it, right? So rotational inertia is a thing, and that's why it's important that we have a massless pulley for our simplification. Because once a wheel starts going, it tends to keep going. Okay, and if you want to test it, turn your bike upside down and spin the wheel of the fickle fingers of fate. We'll see if you still have fingers at the end of it. All right, so if we have a system like this, we've made all these assumptions, that's all good. I want to think about drawing free body diagrams. Notice that I haven't addressed any questions yet. Part A hasn't even come up yet. I just want to, on autopilot, draw a free body diagram. So I'm going to think about mass 1. Mass 1 is going to have a force due to gravity acting downwards on it. what would be acting upwards on it? I'll tell you right now. Yeah? Tension. I'm so glad you said tension because I feel like it's a 50-50 shot. There's going to be somebody that says the normal force. That's not a normal force. Notice that that's not sitting on a solid surface. There's not a contact force underneath of it. That's not a normal force. He said tension though, okay? So we're going to say that there's a tension force, but I actually do want to be even more specific about it. We were saying tension, but we were also using the notation of force of 1 on 2 and force of 2 on 1. So rather than saying tension force, what is this? Force of 1 on 2 or 2 on 1? 2 on 1. I want to call it force of 2 acting on 1. Now, I could do my math on the force due to gravity. Force due to gravity acting on 1 is mass 1 times acceleration due to gravity. That's always how we calculate force due to gravity, the object's mass times acceleration due to gravity. So I'd say, well, actually, you know what, before I do this, I should think about the reference frame. Because I got to do some math. If I got to do some math, then there's going to be some positives and negatives involved. If I think about the reference frame for this guy, notice that my reference frame goes around a corner. Is up positive or negative? I'm going around this way, around the system. Is up positive or negative? Yeah, positive, yeah. I'll just label it as positive and negative, but I won't call them up and down. Instead, I'm going to call them right and left, because that actually matches my reference frame. Anyway, the reason I bring that up is it seems like I should think about negative signs when I sub in my values. So my mass 1 is 2.0 kilograms according to my diagram. And according to my reference frame, the acceleration due to gravity is going to be acting to the left, so down. Well, so negative, I should say. 9.81 meters per second squared. And 2 times 9.81, 19.62 newtons. And the negative from the 9.81 carries forward to the negative 19.62 newtons. Okay, well, fair enough. I want to leave this just for a second because I actually don't know how to calculate force of 2 on 1 just yet. I got to do a little bit more thinking on that. But I do want to do the free body diagram for mass 2. Mass 2 is going to have a free body diagram, and it's going to, of course, have force of gravity acting on 2. And it seems to me that if there's a force of 2 acting on 1, there's going to be what? Yeah? 1 on 2. Now here, I'm going to draw this up because when I look at the picture, I can see that it would be transmitted through the rope, force of 1 acting on 2. But then there's going to be people that say, wait a minute, Newton's third law says that the action-reaction forces have to be equal but opposite in direction. And the way you've drawn the picture, they both are in the same direction. Is that really opposite? Well, it is, yeah, when you think about the reference frame. Let's think about this reference frame. For the reference frame for this object, I'm going to put it out there that that's to the right. Down is to the right. Up is to the left. Which of those guys is positive, the bottom one or the top one? Bottom. Right is positive, left is negative. Notice that they're consistent with my diagram. They look like they're opposite, but my thinking brain knows that they're saying the same thing, okay? And so since left is negative and right is positive, those guys really are opposite to each other. We haven't broken Newton's third law, no funny business, okay? It's just going around a corner. Now, if I was going to calculate FG2, I can say, okay, well, FG2 is equal to mass 2 times acceleration due to gravity, sub in my values, 6.0 kilograms, according to my diagram, times 9.81 meters per second squared. And again, if I want to acknowledge my reference frame, this time that 9.81 is actually a positive value because down is positive on this right diagram, on my mass 2 diagram, I should say. A little bit of math later, I end up getting 58.06, and I'm sorry, this is just one that I've done a few times before. 6 times 9.81 is something I've done a lot of for some reason. What a weird thing. But the value is positive, okay? Propagates forward from the acceleration due to gravity being positive. Yes, sir?
Wouldn't the answer be 58.86?
Oh, shucks, you're right, 58.86. Thanks for catching me. My coffee-addled brain. Okay. All right. So I want to actually try and solve this question, I guess. So it says, find the acceleration of the system. The acceleration of the system, well, there's a couple ways we could think about the system. One way to think about the system is kind of like this great big schloopy thing that like hangs over a pulley. And in that case, if I think of the system as being like a large object that hangs over a pulley, the forces that are driving this system, Fg2 and Fg1, can you see that Fg1 and Fg2 are the only forces actually driving the system? Force of 1 on 2 and force of 2 on 1 are what they call internal forces. Those forces are what's holding the system together. But the external forces, the forces that are either speeding the system up or slowing it down, would be these two guys. And it's almost like there's this around the corner tug of war that's happening. You see what I mean by that? Like, I don't know, a noodle hanging over top of a pulley, if you like. Okay? So that's one way to talk about it. Another way to talk about it is to say, hey, wait, I would like to think of this not as a noodle hanging around a corner, but recognize that this is kind of like a single object that's experiencing a tug of war, where the tug of war that's pulling in two opposite directions is actually Fg2 pulling it to the right and Fg1 pulling it to the left. In that case, I'm just thinking of gravity as being a force that's trying to pull back and forth one way or the other. And I know that one of them kind of looks more like the actual object, and one of them kind of like makes gravity seem like an outward stretching force. Either way is fine. Both of them let us think about reference frames. Now, the around the corner one, I've already done a reference frame for that. If you decide to make it linear, then we would just be saying right is positive and left is negative. Different people like to visualize it different ways. And that's the only reason I'm presenting it this way. And your brain is going to settle on one of those, okay? It doesn't matter to me which one. Now, for the whole system, though, regardless of which way we envision this, the mass of the system, mcis, is going to be mass 1 plus mass 2. And in this case, that's 2 kilograms plus 6 kilograms, 8 kilograms. Looks like we're actually dealing with two significant figures in the givens there. That's fine. But we can say, if I want to find the acceleration of the system, we always fall back on Newton's second law. F net for the system, F net acting on the system, is equal to the mass of the system times the acceleration of that system. Remember, I'm trying to find the acceleration of the system. If I isolate to get acceleration of the system all by itself, then that's F net cis divided by the mass of the system. I don't know what F net cis is off the top of my head. What I do know is that based on either way of envisioning this tug of war, F net cis is going to be Fg1 plus Fg2. Remember, I'm using a force diagram to come up with an equation. And the mass of the system is going to be mass 1 plus mass 2, which I already figured out was 8 kilograms. Give myself a little constructive partition there. Come back up to the top. And I want to start plugging in some values. So the acceleration of my system would be equal to Fg1. Now conveniently, we already calculated this. Fg1 is negative 19.62 newtons. Remember that negative sign matters. It came from the reference frame. It matters. Plus 58.86 newtons. Again, that positive sign matters. And we already figured out mass 1 plus mass 2 was 8 kilograms. So I'll just write it as 8 kilograms now. We could have written it as 2 plus 6. And if I do a little bit of calculating here, can you guys help me out? Somebody with a calculator. What's negative 19.62 plus 58.86? Got it? 39.24. Then 39.24 divided by 8. Yep. 4.90 what? Beauty. 4.905 meters per second squared. And direction-wise, I would say since this is positive, I would say that it's to the right. Now it does look like we have to round this off to 3 significant figures. And this is one of those annoying things where it ends in a 5 and the 5 is the only thing I'm trying to eliminate. It's like that rare situation where this rounding rule happens. And so we have to round it off to 4.90. Round even. There's nothing after the 5 to tip the scales up to 4.91. What a strange rounding rule. Okay? That might even been only the second time all semester we encountered it, right? And we could write a therefore statement. Therefore, the acceleration of the system is 4.90 meters per second squared. But again, I've written too large to fit in that writing. I want you to be able to see it. All right, so B, it says find the net force on each individual mass. And actually, this is already sounding repetitive of the last problem that we did, because it is. It's quite repetitive. What we said in the past was, if I want to find the net force on each individual mass, I could draw the free body diagram for each mass. So for object 1, it would be Fg1, force of 2 acting on 1. And I'll give myself a little divide down the middle line for layout. I could do the same thing for object 2. I'd have Fg2 times force of 1 acting back on 2. But for each of those free body diagrams, a free body diagram is always equal to the Fnet. Fnet 1, Fnet 2. And just a reminder that free body diagrams are a way to generate formulas. However, another way to find Fnet for a mass is to use Newton's second law. So if I know that I want to find Fnet 1, and I know the mass of object 1, and I know the acceleration of object 1, I could just calculate it. Keep in mind that for our system, because it's rigid, we said that at the beginning, the acceleration of the system is equal to acceleration 1, which is equal to acceleration 2. It's all moving together. So when I go to find Fnet 1, I'm going to plug in my mass 1, 2 kilograms, 2.0 kilograms really, times 4.905, the unrounded value, meters per second squared. And remember, that 4.905 really is a positive value because we've declared to the right to be positive. And 2 times 4.905 ends up being positive 9.81 newtons. Now there's always going to be somebody out there who's like, what, 9.81? That's the same numbers as gravity. Don't get excited. It just happened to work out that way because of the numbers I chose, okay? So don't think that there's some hidden secret pattern or Da Vinci Code or one of those sort of things, okay? It just happened, that's the numbers. All right, so 9.81 newtons. And we could even say it's 9.81 newtons to the right. That's the Fnet. Go over to this guy over here. We say, all right, well, we could use the free body diagram, or we could say Fnet 2 is equal to mass 2 times acceleration 2. And we know acceleration 2, we know mass 2. Mass 2 is equal to 6 kilograms times 9.8, no, not 9, oh, I almost hurt my own brain there. 4.905 meters per second squared. And 6 times 4.905, somebody help me out.
29.43.
What'd you say?
29.43.
Nice. 29.43 newtons. And we could round it off to about 29 newtons. Or is it 2 sig figs or 3 sig? I guess it's 2. Okay, because 6.0. So it's approximately 29 newtons. And I guess I really should have called this just approximately 9.8 newtons to the right. I forgot to round to significant figures there. So 29 newtons approximately, because it's positive, to the right would be the net force. Now the next question is to find the tension. Now every time that I find tension, just a quick little note, the tension, Ft, is equal to the magnitude of force of 1 acting on 2, which is equal to the magnitude of force of 2 acting on 1. They're all going to be the same size of force. I know force of 1 acting on 2 and 2 on 1 will be opposite directions. We can see that in the diagrams, but the magnitude is what we call the tension. Okay? So we've got my free body diagram. I think I'm going to draw it a little bit bigger just because I want to have it easily seen here. And I've got force of 2 acting on 1. This is for object 1. Force of 2 acting on 1. I've got force of gravity acting on 1. Those two forces aren't necessarily the same size. I'm just drawing them with no scale in mind. I've got to the right being positive. I've got to the left being negative. I'm just borrowing this from my earlier thinking. And I've got that whole picture being equal to F net 1. So I come up with this equation based on that diagram. I say F net 1 is equal to, I'll just take my vectors, force of 2 acting on 1 plus force of gravity acting on 1. And what am I trying to find here? I'm trying to find tension. So I'm trying to get force of 2 acting on 1 all by itself. Force of 2 acting on 1 is equal to F net 1 minus FG1. Now today I happen to have already done the figuring on F net 1. F net 1 unrounded was 9.81 newtons, and it was to the right, so it's positive, minus FG1, and I'll just like scan up to the top of the page here, which was negative 19.62 newtons. So the minus is from the formula, but then I've also got a negative from the original reference frame, 19.62 newtons. So I'm just emphasizing that negative sign is there because of earlier work with reference frames. And somebody help me out. What's 9.81 plus 19.62 newtons? Yes, sir.
29.43.
Nice, 29.43 newtons. And then, of course, we could round this off to two significant figures, so approximately 29 newtons. And since it's to the right, or since it's positive, it's to the right. Now that could be our answer. We could just say, well, the answer is 29 newtons. The tension is 29 newtons. But I want to do a quick check. Now on a test, I probably wouldn't do this check because I don't want to waste time. I want to get on to the next question. But for the purposes of just like showing that it all works out, look, if I got my free body diagram for my other object, Fg2, force of 1 acting up on 2, my reference frame from this other object, to the left is negative, to the right is positive. All that picture is equal to F net 2. By the exact same format of thinking, I could say, all right, well, that picture generates this equation. F net 2 is equal to force of 1 acting on 2. Notice, 1 on 2, not 2 on 1. F net 2, not net 1, but similar thinking, plus force of gravity acting on 2. And I want to get force of 1 acting on 2 all by itself. So F net 2 minus Fg2. I sub in my values, and again, I happen to have already done this calculation. So F net 2 unrounded was 29.43 newtons, positive 29.43 newtons. Minus, and again, I'm going to scan up to the top of the page. And I got Fg2 being positive 58.86 newtons because of reference frames, as discussed. So let's say 29.43 newtons. I could say minus positive 58.86 newtons. Nobody would really throw in that extra positive sign normally, but I'm just going to do it now just to make sure that everyone knows that we all know that it really is positive. And somebody with a calculator, help this guy out. What do you get? Negative 29.43 newtons. Beautiful. And then we round that off to 2 sig figs. Negative 29 newtons. Oh, and I guess we should give it a reference frame. So 29 newtons to the left. And I think to myself, oh my gosh, Newton's third law is real. You know? And that's a nice thing to be able to get that confirmation. Now, typically on a test, like I say, I wouldn't take the time to do that check. I would just move on to the next question. And so I'm not coaching you to do that in an evaluation situation. I'm just saying that it definitely works out. I could have done it either way. I could have chosen either object to get the right answer, okay? So it just takes the guesswork out of it. If you're doing homework and you want to do checks like that, I encourage you to do that. Just make sure that you really do have it right. Or you can check the solutions too.